and welcome back to the stiffness method. In this session, we will solve another beam example, but this time with the emphasis very much on the coding. So expect a full example, step by step, and some verification checks at the end. Let's get on to it. In this slide, we're recapping the overall workflow for calculating reactions and internal forces using the stiffness method. We've already covered the theory behind each of these steps in earlier lectures, including the stiffness matrices, global assembly, boundary conditions, and solving for displacements and forcements. Here the focus shifts to implementation, translating that process into a structured MATLAB workflow. We start by defining the structure, calculating element stiffness matrices, then assemble the global system and apply the boundary conditions. Once solved, we recover the nodal displacements, support reactions, and internal forces, and finally, we check equilibrium. So this slide is simply a summary of the full method we'll now implement in code. On this slide, we're outlining the full workflow we'll follow when coding the stiffness method for this beam example. All of these steps come directly from the theory we developed earlier, but the aim here is not to revisit the theory, it's to show how the full method is implemented in a clear, structured MATLAB script. You'll notice that all of the input data is grouped at the beginning, including geometry, connectivity, properties, loading, and boundary conditions. That doesn't change the method at all. It simply makes the code easier to read and adapt. From there, we compute the element geometry, form the local stiffness matrices, transform them to global coordinates, and assemble the global stiffness matrix and load vector. We then solve for the nodal displacements, recover the support reactions and internal forces, and finally report the results. This is the workflow we'll now follow step by step. And this is the full beam example we'll be analysing throughout the coding portion of this lecture. The beam spans 10 meters with supports and loading as shown. It includes a 10 kN point load and an 8 kN per meter distributed load, and an inclined 15 kN load acting at 60 degrees. All members share the same cross-section, a 200 by 300 mm cross-section, with a modulus of elasticity of 25 gigapascals. The key point here is the beam is statically indeterminate, so equilibrium alone is not sufficient. Compatibility must also be satisfied. And this makes it a suitable example for the stiffness method, which naturally incorporates both equilibrium and compatibility throughout the displacement formulation. In this lecture, we'll apply the full workflow and implement the solution step by step in MATLAB, and will then verify our results. Before we start defining any structural data, the first step is preparing the MATLAB file. This is mostly housekeeping, but ensures that each run starts from a clean, predictable state. So we clear the workspace, close any open figures, and clear the command window to avoid any interference from previous runs. We also add a simple header to label the example in units, which is always useful as you build up a library of scripts. Here we begin entering the input data for the beam. The first part is the node coordinates. Each row defines a node number and its position along the beam. For example, node 1 is placed at 0 meters, node 2 at 2 meters, and node 3 at 4 meters, and so on. We typically take node 1 as the origin, at 0, simply as a convenience reference point. The absolute position doesn't matter. Together, these coordinates fully define the geometry. Below that, we define the element connectivity. Each row specifies which two nodes are connected by an element. For example, element 1 connects node 1 to node 2, element 2 connects node 2 to node 3, and so on along the beam. This tells the code exactly how the structure is assembled and how the elements are linked together. Getting this step right is essential because everything that follows, the geometry, the stiffness matrices, and internal forces, depends on this information. In this step, we assign the degrees of freedom to each node of the beam. For a 2D beam element, each node has 3 degrees of freedom: horizontal displacement, vertical displacement, and rotation. So we set the number of degrees of freedom per node to 3. We then determine how many nodes and elements we have based on the input defined earlier. The loop shown here automatically assigns degree of freedom numbers to each node. For example, node 1 is assigned degrees of freedom 1, 2, 3, node 2 gets 4, 5, and 6, and this continues sequentially along the beam. The table on the right is the result of this process. Each row corresponds to a node and lists its 3 associated degrees of freedom. And the diagram below shows how these degrees of freedom relate to the physical behavior, with translations and rotation at each node. This numbering is essential as it defines how each element connects into the global stiffness matrix and links the local element behavior to the full structural system. In this step, we define the material and section properties for the beam elements. These values feed directly into the stiffness matrices we derived earlier. Here we're using a modulus of elasticity of 25 gigapascals, which is typical for concrete, and we convert this into pascals to stay consistent with SI units. The same value is assigned to all elements. Next, we define the cross-sectional area using the rectangular section we were given earlier. We convert it into square meters and apply it to each element. We then define the second moment of area, which governs the bending stiffness. For a rectangular section, this is calculated as b times h cubed divided by 12, and again converted into meters to the fourth. The key point here is that while the geometry defines the shape of the beam, the material and section properties control the stiffness, and therefore how it responds to loading. Now we define the loads acting on the beam. As before, grouping all loads at the start makes the code much easier to modify and reuse. There are two types of loads in this example. First, nodal loads. These are forces applied directly at a node. We have a 10 kilonewton downward force at node 2, which appears as minus 10,000 newtons in the global y direction. We also have a 15 kilonewton inclined load at node 5. We need to resolve this first before we can input it, and we resolve it into its components, so 15 times sine 60 in the vertical direction and 15 times cosine 60 in the horizontal direction. Both act in the negative directions, so they appear as negative values in the input. The format used here is node, horizontal force, vertical force, and moment, so additional forces or moments could be included if needed. Second, we define the uniformly distributed load. This acts along an element rather than at a node and is defined in the local coordinate system. In this case, we apply an 8 kilonewton per meter downward load on element 3, which is entered as a negative value. This distributed load will later be converted into equivalent nodal forces when we assemble the global load vector. And the final piece of input data before solving are the boundary conditions. These define which degrees of freedom are restrained, and in other words, which displacements are set to 0 due to the supports. For this beam, the supports provide vertical restraint at nodes 1, 3, and 6, and horizontal restraint at node 1. In the code, we specify these by listing the corresponding degree of freedom numbers. Using the degree of freedom mapping matrix, we can directly reference the required entries. For example, n of 1, 1 or n of 3, 2. This tells the code exactly which degrees of freedom are fixed and should be removed from the system of equations. Getting the boundary conditions right is essential as they directly affect the displacements, reactions, and internal forces. With these defined, we now have all the inputs needed to proceed with the stiffness analysis. Now that all the input data has been defined, the first computational step is to determine the geometry of each element. This includes the element length and direction cosines, which describe how each element is oriented in the global coordinate system. We begin by creating arrays to store the length, cosine, sine, and angle for each element, and then loop through the elements using the connectivity defined earlier. For each element, we extract the coordinates of its start and end nodes and compute the horizontal and vertical differences dx and dy. The element length is then calculated as the square root of dx squared plus dy squared. From this, we obtain the direction cosines as dx divided by the length and dy divided by the length. These are essential for transforming the element stiffness from local to global coordinates during assembly. We also store the element angle using a tan 2 of dy and dx in radians. Once this step is complete, the geometry of the structure is fully defined for the stiffness calculations. Here, we compute the local stiffness matrix for each element. This is a 6x6 matrix that captures both axial and bending behavior in local coordinates, as derived in the earlier lectures. Each node has 3 degrees of freedom: horizontal displacement, vertical displacement, and rotation. So each element has 6 in total. The matrix includes axial stiffness terms EA over L and bending stiffness terms involving EI over L cubed and EI over L squared and EI over L. We carry this out inside a loop so that the same calculation is repeated for every element. For each one, we take its length, area, and second moment of area and use these to build its stiffness matrix. The result is stored in a 3-dimensional array where each slice corresponds to a different element. The first 3 rows and columns correspond to the start node and the next 3 to the end node. This matrix describes how each element resists deformation in its own local coordinate system. In the next step, we'll transform it into global coordinates so that all elements can be assembled into the full structural system. Now that we have the local stiffness matrix for each element, the next step is to rotate it into the global coordinate system. Each element is defined in its own local axis, but the structure is assembled in the global x and y coordinates, so we need to transform between the two. This is done using the transformation matrix built from the cosine and sine of the element angle we calculated earlier. Inside the loop, we form this 6x6 transformation matrix for each element using the direction cosines. We then apply the transformation by taking T transpose and multiplying by the local stiffness matrix, and then multiplying by T again. This rotates the element stiffness from local to global coordinates, ensuring that all stiffness contributions are aligned correctly for assembly. The diagram shows this clearly. The element is inclined at an angle, and we use cosine theta and sine theta to resolve its behavior into the global directions. Once this is done for every element, we're ready to assemble the global stiffness matrix. With all element stiffness matrices now expressed in global coordinates, we can assemble them into the global stiffness matrix for the entire beam. This is the key step where the behavior of all elements is combined into a single system. First, we determine the total number of degrees of freedom as the number of nodes multiplied by 3, and use this to initialize the global stiffness matrix as a square matrix. We then loop through each element. For each one, we extract the global degrees of freedom associated with its two end nodes, giving 6 degrees of freedom in total. These degrees of freedom tell us exactly where the element stiffness matrix should be placed within the global matrix. The code then adds each element's contribution into the corresponding rows and columns of the global stiffness matrix. This process automatically enforces compatibility between the connected elements and ensures equilibrium across the structure. Once assembled, the global stiffness matrix represents the full behavior of the beam, and we're ready to apply the loads and boundary conditions. In this step, we begin assembling the global load vector, which contains all external forces and moments arranged according to the global degree of freedom numbering. We start by creating a zero vector with one entry for each degree of freedom, and then add the loads one by one. The code includes a simple safeguard to check whether nodal loads or distributed loads have been defined. If either is missing, it assigns an empty list, so the script can run without errors for different problem setups. We then loop through the nodal loads. Each row defines a load, giving the node number, the horizontal force, the vertical force, and any applied moment. Inside the loop, these values are placed into the correct positions in the global load vector using the degree of freedom numbering matrix. So each force is applied to the appropriate degree of freedom. In this example, we have a 10 kilonewton downward load at node 2 and a 15 kilonewton inclined load at node 5, already resolved into horizontal and vertical components. As the loop progresses, any loads acting at the same degrees of freedom are automatically combined. At this stage, the global load vector contains only the nodal contributions, and the distributed load will be added on in the next step. In this part, we include the effect of the uniformly distributed loads by converting them into equivalent nodal forces. Unlike nodal loads, a distributed load acts along an element, so it can't be added directly to the global load vector. Instead, first we compute the fixed end forces for each loaded element in its local coordinates. The code begins by creating a container to store these local force vectors for every element, even if some elements have no distributed load. We then loop through the distributed loads. Each entry gives the element number and the load intensity defined in the local y direction. A downward load therefore appears as a negative value. For each element, we calculate the fixed end force vector using the standard expressions. For example, the shear terms are W times L divided by 2, and the moment terms are W times L squared divided by 12. These forces represent the effect of the distributed load at the element ends. Next, we rotate this local force vector into global coordinates using the same transformation matrix as before. And finally, we add these contributions into the global load vector at the appropriate degrees of freedom. At this point, the global load vector contains both the nodal loads and the equivalent forces from the distributed load, so the full loading is now expressed in global form. At this stage, we have everything we need: the global stiffness matrix, the global load vector, and the boundary conditions. Our goal now is to solve for the nodal displacements. We begin by identifying the free and restrained degrees of freedom. The set difference operation gives us all degrees of freedom that are not fixed by supports. Using these, we extract the reduced stiffness matrix and load vector corresponding to the system KFF times DF equals FF. We then solve this system using MATLAB's backslash operator, which gives us the unknown displacements at the 3 degrees of freedom. And next, we reconstruct the full displacement vector. Restrained degrees of freedom are set to 0, and the solved values are inserted into the appropriate positions. The result is the complete displacement vector describing the deformation of the beam. Once this is known, we can move on to computing reactions and internal forces. With a full displacement vector now known, we can compute the support reactions. These are the forces required at the restrained degrees of freedom to enforce the boundary conditions. The calculation comes directly from the global equilibrium equation R equals K times D minus F. This gives the reaction at every degree of freedom, and we can then extract only those corresponding to the restrained degrees of freedom where the supports are located. The internal forces include the axial force, the shear force, and the bending moment along the beam. We begin by creating a container to store the local internal force vector for each element. Inside the loop, we first extract the 6 degrees of freedom associated with the element and use these to obtain the corresponding displacement vector. We then transform these displacements into the local coordinate system using the transformation matrix. Next, we retrieve the fixed end forces from any distributed loads applied to the element. The internal forces are then computed as the local stiffness matrix multiplied by the local displacement vector minus the fixed end forces. This gives a 6-component force vector for each element, representing the forces and moments at both ends. These results can then be used to construct the shear force and bending moment diagrams, or for design checks. And the final step of the workflow is reporting the results. This is where everything we've computed, the geometry, the loads, the displacements, the reactions, and internal forces, printed in a clear and organized format. We first display the global stiffness matrix, mainly just for our verification. We then output basic element information such as lengths, angles, to confirm that the geometry has been defined correctly. Next, we display the global load vector, followed by the nodal displacement vector, which describes the deformation of the beam. We also print the support reactions, which should balance the applied loads, and finally we output the internal forces for each element in local coordinates, including axial force, shear force, and bending moment at both ends. And this completes the full stiffness method workflow from input through to final results. This slide shows 2 key outputs from the analysis: the global load vector and the nodal displacement vector. On the left is the fully assembled global load vector, which includes both the applied nodal loads and the equivalent nodal forces from the distributed load. Each entry corresponds to a specific degree of freedom, and the signs simply reflect the global sign convention. For example, downward forces appear as negative values. On the right is the nodal displacement vector, which is the solution of the stiffness equation. Each entry represents a displacement or rotation at a particular degree of freedom. The values are small, which is expected, but together they define the full deformation of the beam. These displacements are what drive the calculation of the reactions and internal forces. On this slide, we visualize the support reactions calculated from the stiffness analysis. These are the forces that the supports must provide to keep the beam in equilibrium under the applied loads. The numerical values are shown on the left, and each corresponds to a restrained degree of freedom at the supports. The signs follow the global sign convention, but in the diagram the arrows are drawn in their true physical directions so that negative values have been flipped for clarity. You can see that the central support carries the largest vertical reaction as it supports most of the distributed load, while the end supports carry smaller reactions depending on the loading and geometry. The results shown at the bottom of the slide are from F-Tool, which is a free structural analysis software, and you can see that they match closely with the values obtained from the code. This kind of comparison is an important part of verification and validation. It gives confidence that the implementation is correct and that the modelling assumptions are consistent and the results can be trusted. In practice, checking against a second method or software is a key step in any structural analysis workflow. On this slide, we're interpreting the internal force values obtained from the program, shown in the table at the bottom. These forces are expressed in local coordinates using the same sign convention defined earlier, moving from the first node to the second node of each element. All forces and moments shown on the diagram are drawn in their true physical directions. That means that if the computed value is negative, the arrow has been flipped so that it represents the actual behavior of the element rather than just the sign of the number. Positive values follow the defined sign convention, while negative values are adjusted for clarity in the diagram. It makes it much easier to interpret the behavior compared to reading the numerical output alone. The diagrams show the axial forces, shear forces, and bending moments at each element end. And on the next slides, we'll look at these components individually to better understand the structural response. On this slide, we're comparing the axial forces obtained from the stiffness method to the results from F-tool. What you see at the top is the interpretation of the axial force values from our code, drawn in their true physical directions. Compression is shown pushing into the element and tension pulling away, so any negative values have already been flipped for clarity. It's important to note that this slide shows only axial forces. The external loads in red and the reactions in purple are included for reference, but the structure is not in full equilibrium here, as shear forces and bending moments are not shown. Pattern is consistent with the applied loading, with the central region carrying the highest axial force and the inclined load introducing horizontal effects along the beam. At the bottom, the same axial forces are plotted using F-tool, and you can see that the results match exactly in both magnitude and distribution. This provides strong validation of the implementation and confirms that the axial force component has been extracted correctly from the stiffness solution. Here we are looking at the shear forces from the stiffness method code and comparing them with the results from F-tool. The values at the top are the interpretation of the shear forces from our MATLAB results drawn in their true physical directions. Positive shear follows the local sign convention, and any negative values have been flipped so that the arrows represent the actual internal action. As with the axial results, this slide shows only the shear forces. The external loads in red and reactions in purple are included for reference, but the structure is not in full equilibrium here, as bending moments are not shown. Looking at the shear equilibrium in the MATLAB results, we can see that the forces balance correctly within each element, with changes in shear corresponding directly to the applied loads. The distributed load produces the expected variation along the span, and the point load introduces a clear jump in the shear. At the bottom, the shear diagram from F-tool is shown, and the results match exactly in magnitude, sign, and distribution. This confirms that the shear forces have been computed correctly, and the implementation is capturing the shear behavior of the beam as expected. And on this slide, we're looking at the bending moments from the stiffness method code and comparing them with a moment diagram from F-tool. The values at the top are the interpretation of the moments from our MATLAB results, once again drawn in their true physical sense. Any negative values have been flipped, so the arrows show the actual bending behavior. As before, the slide only shows moment, so the external loads and reactions are included, but the structure is not in full equilibrium without shear forces. Looking at the moment equilibrium in the MATLAB results, the variation in bending is consistent with the loading. The distributed load produces a smooth curvature, while the point load introduces a change in the slope of the moment diagram. The largest moments occur in the central region, under the distributed load, with the smaller moments towards the support, which is exactly what we expect. At the bottom, the bending moment diagram from F-tool is shown, and the results match exactly in magnitude, sign, and overall shape. This confirms that the bending behavior has been captured correctly, including the rotational degrees of freedom and the contribution from the distributed load. And on this slide, we're looking at the nodal displacements from the stiffness method code and comparing them with the deformed shape from F-tool. The values shown on the right are the displacement vector for MATLAB. Here we're focusing on the vertical displacements at each node, which define the deflected shape of the beam. These values are very small as expected, but they capture the full deformation behavior of the structure. The curve shown represents the deformed shape, scaled for visual clarity. You can see the beam deflecting downwards under the distributed load, with changes in slope at the supports and locations of point loads. The displacement is zero at the supports, where the vertical movement is restrained, and reaches the maximum in the central span, which is consistent with the loading. Comparing this with the F-tool result, the shape and relative magnitudes match exactly. And this confirms that the stiffness formulation, boundary conditions, and load implementation are all working correctly, and that the displacement solution is accurate. You can, of course, use different methods to verify and validate, and obviously different computational programs. I've used F-tool here because it's free and easy to use, but obviously you can use any other computational software or any other method to validate. The main thing is, the first time especially that you write a code, you want to make sure that there are no mistakes, and this method of validation is a great way to verify your code. Thanks for joining me. This concludes this full beam setup, coding, and validation example. I hope this helped, but what I would recommend is looking for other beam examples, putting them in the code, and seeing how it all works together, obviously along with some verification. That's when it all starts to click.